So now let's talk about quadric surfaces. So quadric surfaces are solution sets to degree 2 polynomial equations in the three variables x, y, and z. So a degree 2 polynomial equation means that we are looking at sums of products of powers, whole number, non-negative powers of x, y, and z. And degree 2 specifically means that the power on x, y, and z is at most 2, or if we have x times y or x times z or y times z, the sum of the powers on them is at most 2. So that really boils things down to 10 possible sorts of terms. X squared, y squared, z squared, xy, xz, yz, xyz, and a constant. And for these to be at all interesting, we're assuming that a, b, c, d, e, and f, which are just coefficients of these different terms, are all not, or are at least one of them is non-zero. Because if they were 0, we would just have this, and this we should recognize as the equation of a plane. We already talked about planes. We'd like to talk about something different now. So by rotation and translation, we can take any quadric surface and we can spin it around in space. Rotation, we can move it around in space. Translation, but we don't stretch it or shrink it or do anything weird to it. Don't rip it up or anything. Just keep its shape. Just move it around nicely in space. We can get to one of the following possibilities. We can, and I'm going to talk about it in terms of how the equation is altered. First, we might be able to get rid of one of the variables altogether. Just have an equation and say x and y. This gives us a cylinder. Specifically here we get a cylinder of a conic section. And what are conic sections? Well, they are intersections of cones, really of two cones, sort of placed like this. An intersection of a cone with a plane, which gives you things like hyperbolas and parabolas and whatever. So you have parabolas, or familiar graph of a quadratic function, ellipses, which look like that, hyperbolas, and pairs of lines. All right. Now, and then we take cylinders of those things. Now, we might not be able to eliminate one variable, but we might be able to reduce the power on one of the variables down to just the power 1, but the other two are stuck with the power 2, in which case you can always make it look like this: ax squared plus by squared plus z squared is equal to 0. And here we're assuming that a, b, c, they're not any of them equal to 0. And in this scenario we get things called paraboloids. Just as the parabola is the only conic section which can be written as y is a function of x, these are going to be the only quadric surfaces other than certain cylinders, but the only non-cylinder quadric surfaces where we can write z as a function of x and y. Those are paraboloids. And over here, we might not be able to knock the power down on any of the variables. We're stuck with x squared, y squared, z squared, but it turns out we can get rid of every other instance of x, y, and z. We're just stuck with ax squared, by squared, cz squared, where a, b, and c are all non-zero, possibly plus a constant. And this gives us a few different things. This gives us ellipsoids, which are like 3D versions of ellipses, hyperboloids, which are like 3D versions of hyperbolas, and cones. Specifically, this picture of cones here, two cones touching at their point, which is the appropriate generalization of two intersecting lines like that. So let's start going through all of these different things. First, we have the elliptic paraboloid. Now, this looks like z over c is equal to x squared over a squared plus y squared over b squared. First, just a comment about this particular expression. It looks different from what I had up before. These are all lowercase letters now. That's supposed to be a lowercase c. What is the relationship they have with the coefficients from before? The answer is don't worry about it. Don't worry about it at all. All this is supposed to suggest to you is that a squared and b squared, those are both positive numbers. And c, well, c could be positive or negative. So really, these guys have the same sign on them, and c could be positive or negative. And this gives us something called an elliptic paraboloid. So let's consider one of these guys. Let's sketch z equal to x squared plus y squared over 4. So a great way to sketch something like this is to sketch its traces. And to do that, we set each of the variables equal to a constant and then consider what that sort of graph would look like. So for example, if we set x equal to a constant k, we get z is equal to y squared over 4 plus k squared. That is a parabola. That is a parabola where y is the horizontal axis, z is the vertical axis. So y is playing the role of the independent variable here, z is the dependent variable. And so I've sketched a couple, like literally two, of these parabolas here. So it looks like that. That's one. This one is literally sitting on the origin. Here's another one right here. That's when k is actually positive. Note that as k increases, this gets to be a bigger and bigger number. So really it's just the same parabola but being pushed upward. So, and the same thing happens as we go back. So these vertical slices along x are parabolas. Same idea along y. Even though we're dividing by 4 here, at the end of the day, we've got x squared plus k squared over 4. So when we take the slices in the y direction along y, we get green parabolas like this. Great. So in both vertical directions, we get parabolas. That's why this is a paraboloid. But it's an elliptic paraboloid because when we take these vertical slices, or really horizontal slices of them along the z-axis, we let z be constant, we get x squared plus y squared over 4 is equal to k. This is the equation of an ellipse. Well, so long as k is greater than or equal to 0. If k is 0, we just get a point, which is this origin. If k is greater than 0, we get ellipses, and I've drawn a couple of them. So this is what this guy looks like when you slice it horizontally. Great. This is good enough for our picture of an elliptic paraboloid. You can try harder if you like. But I don't want you to get too much of a headache trying to sketch stuff like this. Just a quick note about elliptic paraboloids. The main behavior that we notice with them is that they could be upward facing or downward facing, opening up or opening down, just like our regular old parabolas. This depends upon whether this number c under z is positive or negative. If c is positive, it opens up. If c is negative, it opens down. Those are our two possibilities, and different values for A, B, and C can make it, wider, narrower in various directions. That's pretty much it.